So, hello students, let's continue from our previous lecture. In the previous lecture, we had seen some basics of the matrix algebra. We require the matrix operations for understanding all our subsequent calculations. And in today's lecture, we will look at the axially loaded one-dimensional systems. We will see how to analyze them. And just a brief brush up on the Gauss elimination method before we go with today's topic. Okay. So, we had seen that if you have system of simultaneous equations with variables x1, x2, x3 and x4, we can solve it by either matrix inversion or by Gauss elimination method. And between these two, the Gauss elimination method we had discussed is more suitable for finite element calculations because we have a banded matrix where significant number of stiffness coefficients away from the diagonal are 0. So, we first convert our system of equations into an upper diagonal matrix like this, so that in the last equation we have only one coefficient, and then we can get the last variable x4 as p4 bar by k44 bar. And once we determine the x4, we can determine x3 from the previous equation, because we have two quantities here, x3 and x4, and x4 was already determined, and now we can determine x3 like this and continue the process x2, x1 and so on. Okay. So, now let us see what are all the quantities that we solve for in any geotechnical problem. The first quantity is displacements. Displacements could be only one when we are dealing with one-dimensional problems, or 2 at each node when we are dealing with the 2-dimensional, and 3 when we are dealing with the 3-dimensional problems. And then we have the pore pressures, okay, and then we have the strains, and then stresses, and then the forces in the support systems or in the soil and so on. Okay. And the primary quantities that we determine are the displacements. Then in the problems with water, we also have the pore pressure, okay, and we determine the strains from the displacements using the compatibility equations, and then we can determine the stresses from the strains using the constitutive equations that we will see later in some other lectures. And we need to set up some equilibrium equations so that we can determine the displacements. Okay. That is some stiffness multiplied by displacement is equal to force, and what we mean by equilibrium equation is the applied force should be exactly equal to the reaction force. Okay. And that is the basis on which we will develop all our equations. And initially we will discuss only the problems with only displacements, that is the elasticity problems, and later we will introduce water and we discuss the poroelastic problems later. Okay. So, let us start from the most fundamental, strength of materials, because all of us are familiar with this famous equation delta is equal to PL by AE. Okay, that is the equation that we study the first thing in any of the strength of materials courses. Let us look at a columnar element of length L and area A, and let its Young's modulus be E, and let us say that we applied a load of P, and we would like to know what is the displacement at the top. Okay. And for doing that, we can do the following. We can determine the stress as the load divided by the area P by A, and then the strain is the stress divided by the Young's modulus, and the stress is P by A and E is the Young's modulus, so P by AE. And once we get the strain, the tip deformation delta is L times epsilon, where L is the length of the element. So, it is L times epsilon is PL by AE, okay. And so, our delta, the tip displacement is PL by AE, or we can also write this in a slightly different form as AE by L times delta is P, or AE by L is P by delta. And let us look at the units for these quantities. See, the units of this product AE by L, A has the units of area L square, E is the force per unit area, the stress F by L square, and the whole thing divided by L. So, that is in the units of F by L, that is the force per unit deformation. And this AE by L is a quantity that we call as the stiffness, and that has the units of force per unit deformation. And on the right hand side also we have the P by delta. P is has the units of force, and delta has the units of displacement or the length. So, it is P by delta. So, both the left hand side and the right hand side, they have the same units, okay. And so, AE by L is our stiffness, and that multiplied by some displacement is equal to the force, okay. And actually we can think of it in some other manner. On the right hand side we have the applied force, that's what we are applying on the system, and AE by L times delta is the reaction force. So, at some point the reaction force should be exactly equal to the applied force, okay? And that is what we call as equilibrium, okay? And so, what we mean by the equilibrium is externally applied force should be exactly equal to the internal force of the reaction. That is, reaction is developed by the body to resist the applied forces, okay? And so, any force that we apply on the system will produce some deformations that we may be able to measure with a ruler or with a micrometer or something, depending on the magnitude of these deformations, okay. And this body will go on deforming until an equal and opposite force is applied, force is developed to oppose the applied forces, right. And if the body is very soft, equal and opposite reaction force is developed at a large deformation, and if the body is stiff, equal and opposite reaction is developed at a small deformation. So, that explains why if you have a very stiff spring and you apply some force, it will deform very little, but if you have a soft spring, it will deform by a larger amount. And the governing principle is they will deform until an equal and opposite force is developed to oppose the applied force, okay. So, this stiffness coefficient is required because we require to calculate the reaction force, that is calculated as stiffness times displacement, and that is equal to the applied force on the right hand side, okay. Or the stiffness is a force divided by the displacement, okay. And in general we define a stiffness coefficient Kij. Actually we are going to deal with the multi degree of freedom system. So, we have to develop these systems for large number of displacements or the degrees of freedom, and our stiffness coefficient Kij is defined as the force developed in the ith degree of freedom DOF due to a unit deformation applied in the jth degree of freedom. So, we apply some unit displacement in one direction, and then what is the reaction force developed in the I direction, that is called as the stiffness coefficient. And while we are doing this, we constrain all the other degrees of freedom. Okay, that is the basic definition for Kij, and let us try to develop these coefficients for simple systems before we go on to the continuum, that is our soil. Okay. And let us start with one dimensional bar element that is purely axial. All the deformations are only in the axial direction, and also the forces are in the axial direction, either tension or compression. And let us consider a simple one dimensional 2 node bar element with the 2 nodes, node 1 and node 2, and 2 deformations u1 and u2, and 2 applied forces p1 and p2. Okay. And this element has nodes at 1 at each end. So, node 1 on the left end, node 2 at the right end. Okay. And this element has 2 axial degrees of freedom u1 and u2, and then 2 axial forces p1 and p2. Okay. And since we have 2 degrees of freedom, this element will have 2 equilibrium equations, that is reaction at node 1 R1 should be exactly equal to P1, and the reaction at node 2 should be exactly equal to the applied force P2. Okay. And let us say that our stiffness is AE by L, where A is the cross sectional area of the element, E is the Young's modulus, and L is the length of the element. Okay. So, let us apply unit deformations in different directions and then measure the forces, so that we can define our stiffness coefficients Kij. And to start with, let us apply a unit deformation at degree of freedom 1, that is u1 is equal to 1, and while we are doing that, we constrain this node or this degree of freedom u2 to 0. Okay. And so, the unit deformation at 1 will produce a force equal to AE by L times 1, because AE by L is our stiffness that is related to the force through the displacement. Okay. So, at degree of freedom 1, the force developed is AE by L, and by definition the corresponding stiffness coefficient is K11, that is the force developed in degree of freedom 1 when a unit displacement is applied in the same degree of freedom 1. Okay. And the force developed is K11, that is AE by L. Okay. And at node 2, equal and opposite force should develop to maintain the equilibrium. Okay. And at node 2 at the degree of freedom 2, the stiffness coefficient will be K21. The force developed at the degree of freedom 2 because of a unit displacement applied at degree of freedom 1. Okay. So, that K21 will be or needs to be equal to minus AE by L, so that we have equal and opposite reaction force at the other end. Okay. So, the force developed at degree of freedom 2 is minus AE by L due to a unit displacement at degree of freedom 1. Okay. And similarly, we can apply a unit displacement at a degree of freedom 2 while we constrain this degree of freedom from moving. Okay. So, by doing this, we can write that K22 is AE by L, that is the force developed in degree of freedom 2 because of a unit displacement at degree of freedom 2. Okay. And the force developed at degree of freedom 1 because of a unit displacement at degree of freedom 2 will be K12, and that should be equal to minus AE by L to maintain our equilibrium. Okay? And otherwise the system will undergo some undue deformations that we call as rigid body deformations. Okay? So, here our K12 is minus AE by L, that is the force developed at degree of freedom 1 because of a unit displacement at degree of freedom 2. Okay? So, by combining these, the internal forces developed can be written like this. The internal force developed at degree of freedom 1 because of displacements u1 and u2 will be K11 u1 plus K12 u2, and as we have seen, K11 is the force developed because of a unit displacement. So, that is the stiffness coefficient, and if you apply a deformation of u1, the force developed is K11 times u1, and similarly the force developed in degree of freedom 1 because of a unit displacement at degree of freedom 2 is K12. So, K12 times u2 is the reaction force developed in degree of freedom 1. Okay? And similarly, the internal force developed at degree of freedom 2 will be K21 u1 plus K22 u2, and these are the internal forces or the reaction forces, and these should be exactly equal to the applied forces P1 and P2. Okay? So, K11 u1 plus K12 u2 is P1, and K21 u1 plus K22 u2 is P2. Okay? And we can write this in a matrix form like this: K11, K12, K21, K22, u1, u2 is equal to P1, P2. P1, P2 are the applied forces, and K11, K12 and all these things are numerical equal to AE by L, and K11 and K22 they are positive quantities because they refer to their own degrees of freedom, whereas K12, K21 are the cross terms, the force developed at some other degree of freedom because of unit displacement at this degree of freedom, and by definition that should be minus. Okay? So, there you go. This is the set of equilibrium equations, and then if you have the material properties, the cross sectional area, Young's modulus, and then the length of the element, we can determine the stiffness coefficients and then get our stiffness matrix, and P1, P2 are the applied forces, these are known, and u1, u2 are the displacements. So, now the question is, so if I give you the material properties and then the applied load, can you determine u1 and u2? That is, can we invert this matrix? Basically, that is what we mean. If we are able to invert this matrix, we can determine u1 and u2. So, we can easily find out if we can invert this or not by doing what? By calculating the determinant of this matrix. So, if you calculate the determinant AE by L multiplied by AE by L minus of these two quantities, and we see that the determinant is 0. So, that means that although we have the system of equations that we need, we cannot solve, and before we solve we need to do something else that we will see later. And now see, we see that our system of equations gives us symmetric stiffness matrix. See, K12 and K21 are the same, minus AE by L, and this symmetry we can imagine by looking at the reciprocal theorem, Maxwell's reciprocal theorem. That is, say if you have a structure with a load applied at one point and you measure the displacement at some other point, or apply the load at the other point and measure the displacement at this point, the delta should be the same. Whether you apply the load here and measure the displacement here, or apply the load here and measure the displacement here. That is the Maxwell's reciprocal theorem, and because of that we see that all our stiffness matrices, they are symmetric. So now let us continue for a larger body of our structure. Let us consider now two elements, element 1 and element 2, and it is not necessary that they have the same cross sectional area and the same properties and other things. Let each one have their own properties. And now we have 3 nodes, node 1, node 2, node 3, and 3 displacements u1, u2 and u3, and the 3 applied forces P1, P2 and P3. And let the stiffness of these 2 elements be K1 and K2, because theoretically each element can be made of different material. They may have different length and different cross sectional areas and so on. And let the displacements be u1, u2 and u3, and the applied forces are P1, P2 and P3. And the equilibrium equations for the 2 elements can be written separately, for element 1 and element 2 separately like this. See, for element 1 that is connected to degrees of freedom u1 and u2, we can write like this: K1 minus K1 minus K1 K1 u1 u2 is equal to P1 P2. Similarly, for element 2, it is connected to degrees of freedom u2 and u3, and the applied forces are P2 and P3. So, this is our system of equations for element 2. And but then our structure has 3 degrees of freedom, and now we have to see how we can develop the equilibrium equations for the entire structure. See, now we have determined the equilibrium equations at the element level at for element 1 and element 2 separately, and we need to form the equilibrium equations for the entire structure, and that we can do by assembly of the contributions from different elements. And so if we assemble, we get the equations for the entire structure. But how? So if you look at the degree of freedom 2 is common for element 1 and element 2. So the displacement is the same at these at this node for both elements 1 and element 2, right? And so it is actually we can think of 2 springs connected in parallel, because these axial elements you can imagine them as spring elements, just spring, because that is what they are. And let us consider that 2 elements K1 and element 1 and element 2 are connected rigidly between 2 platons, and the stiffness of element 1 is K1 and stiffness of element 2 is K2. And when we apply any force, both will undergo the same deformation because they are connected with a rigid platon. The same displacement delta in both the elements, and let us say that the combined stiffness is Ks, that is the contribution from element 1 and contribution from element 2. And so the applied force P is shared by both the springs in proportion to their stiffness. So the force developed in spring 1 is K1 times delta, and the force developed in spring 2 is K2 times delta. And the total force P is P1 plus P2 that is K1 times delta plus K2 times delta. And let us say that our combined stiffness is Ks, and if you look at this, the P is Ks times delta. The Ks is the combined stiffness of the system, and P1, P2 are K1 delta and K2 delta. So, if you look at this, the combined stiffness is K1 plus K2. Okay, that should give us the clue on how to assemble the contribution from these two elements. So, if you assemble a degree of freedom 2, the contribution is added up. So, we have K1 and K2, K1 plus K2, and so this is how we do. Okay, and so this K1 minus K1 minus K1 K1 is the contribution from element 1, and from element 2 we have K2 minus K2 minus K2 and K2, and at this degree of freedom 2 the contributions of both the elements are added together. So, we have this K1 plus K2. So, now the stiffness matrix and the equations, they correspond to the entire structure. Okay? If we are able to solve this system of equations, we can get our unknowns U1, U2, U3. Okay? And so, once again we see that our stiffness matrix is banded and symmetric, minus K1, minus K1, minus K2, K2, and you see a 0 here, and it is not difficult to imagine why we got 0 here. If you look at the structure, see this degree of freedom 3 is not connected to degree of freedom 1. So, if I apply some unit displacement or and some force here, only this the U2 might react because it is connected to U3, but U1 is far away and it is not directly connected to U3. So, our stiffness matrix will look like this: K1 minus K1 0. This 0 just simply means that if we apply anything at degree of freedom 1, the degree of freedom 3 is not affected. Okay? And now let us consider a bigger element, a bigger structure. So, now with 6 elements and 7 degrees of freedom, U1, U2, U3, U4, U5, U6, U7, okay. And now you see the banded nature of this stiffness matrix: K1 minus K1 minus K1, K1 plus K2 and so on, and these are the displacements U1, U2, U3, U4, U5, U6, U7, and then these are the applied forces. And the determinant of this bigger matrix is also 0. That we do not need to doubt, because at one element level we have seen, then we can extrapolate the same thing, and for even for 2 element case where we have a 3 by 3 matrix, we can theoretically calculate and see that the determinant is 0. And if you take a lot of effort and find the determinant of this entire matrix, you will see that it is 0. We do not need to actually calculate. Okay? So, the first thing that we need to notice is that the stiffness matrix is highly banded, okay? And most of the elements are 0, okay, in each column. So, if you apply a Gauss elimination procedure for this system, we just need to eliminate one value below the diagonal in each of these columns. So, it becomes very simple, but then if you have to invert this matrix, you need to spend a lot of time, and the determinant of these matrices is also 0. So, we cannot really do anything. We cannot invert these matrices and find our displacements. And as such, these systems are not constrained and they may undergo rigid body deformations. A rigid body deformation is something very simple. So, I take this pen and move it in the air somewhere, and all the points on this pen are moving by the same amount. So, that means that there is no relative deformation between the 2 points within the pen, and there is no strain within this pen, and if there are no strains, there will not be any internal forces or internal strains. Okay. So, to make this system stable, we need to apply some constraint, at least one constraint, because in a one dimensional system we just require one constraint, and one of the displacements we can fix to some known value. It could be 0 or it could be something else. Okay. So that we can prevent the system from undergoing rigid body deformations. And the rigid body deformation is a deformation such that all the degrees of freedom undergo the same deformation, equal deformation. Okay. And the rigid body deformations as such, they do not create any internal strains, and hence the body is not stretched or body is not stressed. Okay. So, if I keep the pen here or somewhere else, the forces that are developed within the body are 0. Okay. And if the body is not stressed, it will not be able to produce any reaction force. So, we can say that the rigid body deformation does not satisfy our equilibrium equations, because we are applying some external force, but the internal reaction is 0. So, that means that any body that is undergoing rigid body deformations will undergo infinite displacements, because there is no limit on the displacements, because the reaction force is not developed. Okay. So, let us look at conceptually a very simple problem. Let us take one axial element and then go on pulling at the two sides by an equal amount. Okay. And we know that this system is in equilibrium, because we have applied equal and opposite forces at the two ends. Okay. And the solution is obvious to us. The axial force is equal to P, that is the tensile force, and the stress is P by A. Okay. But then if you pose this problem to any computer, it will say that no, it is this system is unstable, because there is no constraint. Okay. Because you cannot really invert the matrices, and these matrices are called as singular matrices, and as such we cannot solve this. And we can do a small trick to make this stable. See, at this neutral point, at the exactly at the mid length of this element, what will be the displacement? See, here at this end, let us say that there is a positive displacement, and at this end it will have an equal displacement, but in the negative direction. And exactly at the midpoint, the displacement should be 0, because that is the symmetry point, and in between we will have a smaller displacement of either positive or negative magnitudes. Okay. So, at the symmetry plane our displacement is 0. So, this is what we can enforce on the system, that at this point my displacement is 0, and then you apply the force and then find the deformations. And once we apply this deformation constraint on the symmetry plane, then we can either solve the right hand side, the half of the problem, or the left hand side. It does not matter, because both will give the same result. Okay. And but then how do we apply some constraints that we call as the boundary constraints, and there are two methods. One is the exact method and the other is the boundary spring method or the penalty method, and I will explain both of them. Very simple. Let's look at the exact method first, and let's say that we have a system of 4 simultaneous equations with 4 unknowns x1, x2, x3, x4, and then the applied forces are P1, P2, P3, P4. Okay? And let's say that one of these degrees of freedom x3 is known to us, or it's constrained to be delta. Okay? And after solving, our delta x3 should be equal to delta. Okay? And in here, if we see, these are all the known quantities k11, k12, k13 and so on, because once you know the geometric and material properties, we can determine k11, k12 and other things. And then on the right hand side, P1, P2, P3, P4, these are the applied forces. So, this also we know, but only thing that are unknown are x1, x2, x3 and x4. Out of this, x3 is known. So, we can actually modify this system of equations and send all the known quantities to the right hand side. Okay? And so that we are left with only the unknown quantities on the left hand side. Okay? And so we can rewrite this system of equations by sending all the known quantities to the right hand side. So, since x3 is known and k13 is known, we can take a product of k13 and x3 and send this to the right hand side, and that will belong to degree of freedom 1. So, it should go to the right hand side in row 1. Okay? And so, our first equation will be k11 x1 plus k12 x2 plus 0 times x3, because k13 we have taken to the right hand side, plus k14 x4 is equal to P1 minus k13 delta. Similarly, the second equation, and then the third equation is actually, it's a trivial equation, x3 is equal to delta. And then the fourth equation is k41 x1 plus k42 x2 plus 0 times x3 plus k44 x4 is P4 minus k43 delta. And our third equation is actually, it's a trivial equation that x3 is equal to delta. So, you might ask, since we already know x3, why do we need to have this in the system of equations? The reason is very simple, because we started with 4 unknowns and 4 degrees of freedom, and one of the degrees of freedom is known, x3 is known, and it is very difficult to program to eliminate 1 degree of freedom suddenly. We started with 4 degrees of freedom, and it is more easy to continue with the same number of degrees of freedom. So, for that reason, we retain the third equation, but with a very trivial equation, x3 is equal to delta, and then our job becomes more simple. Our writing the program becomes very simple, and then if you rewrite those equations in a matrix form, we get like this: k11, k12, 0, k14 and so on, and the right hand side is P1 minus k13 delta, whereas the third equation is just simply x3 is equal to delta. Okay? So, in general, if degree of freedom m is constrained, the changes to be made are kmm is 1 and pi is pi minus kim times delta if I is not equal to m, okay? And pi is delta if I is equal to m, and kmi is kim is 0, that is off diagonal terms. Okay? And once you make these changes, this stiffness matrix, the modified stiffness matrix, is not singular. It will have some determinant, and we should be able to invert this matrix. Okay. So, these are the changes that we make, and then we eliminate these degrees of freedom. Okay. By eliminating this degree of freedom x3, we can do this. Okay. So, if the system has very large number of degrees of freedom, may take a very long time to modify each of these stiffness coefficients and the load vector, and so we should have some other method for applying similar constraints, and that is called as a boundary spring method. Okay. And so, it is also called as a penalty method, because on the system we apply some penalty so that we can enforce what we want. Okay. And what we do is we take an artificial spring of very large stiffness Ks and add it at the mth degree of freedom where we want to apply some constraint, and then apply a force equal to Ks times delta on the right hand side. Okay. So, the advantage is that we make only two changes, one on the right hand side and one in the stiffness coefficient, but the disadvantage is that the accuracy of the solution depends very much on the value of the boundary spring, stiffness. It has to be much larger than the all other stiffness coefficients, so that our result is accurate. Okay. So, that we can see with an example. So, on the same problem, say we are constraining the third degree of freedom to some delta, and we can add the Ks to the diagonal element of this stiffness matrix, and then on the right hand side we can apply a force equal to Ks times delta, and this Ks is so large that compared to all the other forces that are developed, like K31 times x1, K32 times x2, K34 times x4, they are very small and negligible, and so our x3 after doing the calculations will be approximately equal to delta. If provided our Ks is very large, the calculated delta will be the same as what we want, but if our spring stiffness Ks is not of very large quantity, then we could have some errors. Okay, that we can check with a numerical example. Okay. And the accuracy of this solution depends very much on Ks, and if the Ks is very large, let us say the ideally Ks should be infinite, so that at the end of this solution this Ks in the numerator and denominator, they cancel out, and all other quantities are very small, because this is infinite times delta, it is a very large quantity, infinite. Okay. And but then if we make it very large, we could have some round off errors when we are doing the computations. So, we have to have a balance between the computational accuracy and then this boundary spring stiffness that we give. Okay. So, now by doing one of these methods, we can enforce the constraint, or the other method is, if any of the fixed degrees of freedom is there, we can directly eliminate that right from the beginning, and we do not number that particular degree of freedom and assign any stiffness coefficient. Okay. And especially this is typical of geotechnical problems where we have very long boundaries where our displacements are 0, and at the time of the numbering the equations itself, we do not number those degrees of freedom, and that is how we can eliminate those fixed degrees of freedom. Okay. That we will see later, not at this stage. Okay. And so, here let us go back to our two element problem. Okay. And let us say that our u1 is 0, okay, and P2 and P3 are not affected because our u1 is 0, okay. So it is the first row and first column can be eliminated because the P1 is not affected because this displacement is 0, okay. And so we can eliminate the first row and the first column, and we end up with a 2 by 2 matrix like this: K1 plus K2 minus K2 minus K2 K2 U2 U3 and 0 and P, because we applied only one force P at this point 3, okay. So we can solve it either by Gauss elimination method or by matrix inversion method, and we see that our U3 is P by Ks and P times K1 plus K2 by K1 K2, and actually we have seen that this is equal to the spring constant Ks when we have two springs in parallel to each other or in series, sorry, okay. And our K1 plus K2 times U2 minus K2 times U3 is 0. That is, once you get U3, we can get U2 as P by K1, okay. And the Ks is our combined stiffness, K1 K2 by K1 plus K2. And once we get the deformations, we can find the forces in the two elements. The force in element 1 is K1 times U2 minus U1, and the force in element 2 is K2 times U3 minus U2. Okay. And actually, let's look at one small numerical example to illustrate this. Actually, this combined stiffness of two springs in series is explained here, and that I think you can leisurely see. Now let's look at one numerical example so that we can give some values and then understand the calculations better. Let's say in this previous example of two elements with spring 1 K1 and spring 2 K2, we applied a load of 50 at degree of freedom 3, and at degree of freedom 1 we constrained the displacement to 0.3. Okay. And so our equilibrium equations are like this. See, this K1 is 1000 and K2 is 2500. So this is our assembled equations: K1 minus K1 minus K1, K1 plus K2 minus K2, and so on. Okay. And here we know that our U1 is 0.3, okay, and our known quantities we can take to the right hand side, and here it was minus 1000. So minus 1000 times 0.3, if you send it to the right hand side, you get 1000 times 0.3, that is 300. And then at degree of freedom 3, we have applied a force of 50. Okay. And we can solve this by converting this to an upper diagonal matrix, and we get U3 as 0.37, U2 is 0.35, and U1 is 0.3. And that is what we wanted. U3 is fixed as 0.3, and the force in element 1 is 1000 times U3 minus U2. That is the relative deformation, that comes out as 50, and the force in element 2 is 2500 multiplied by 0.37 minus 0.35, and that comes to once again 50 because they are in series. Okay. And let's look at the boundary spring method to illustrate, and let's take the boundary spring stiffness as 10,000. Okay. So, the PS is 3000, 1000, 10,000 times 0.3. So, our original equations are like this, and the modified equations are like this. Okay. And U1 we want as 0.3. So, on the right hand side we applied a force of 3000, and then the left hand side we have added the boundary spring of 10,000 to the first degree of freedom. If you solve this system of equations, we see that U3 is 0.375, U2 is 0.355, and U1 is 0.305, and with the exact method these were the displacements that we got, which are very close to these values. And now let us look at another example. By assigning only 500 to the boundary spring, Ks is 500, okay. And if you solve, we see that our U3 is 0.47, U2 is 0.45, and U1 is 0.4. See, we wanted a U1 of 0.3, but we end up with 0.4, which is totally different. And so actually whenever we use boundary spring method, we have to be very careful in the boundary spring value that we assign, okay. And if we assign a large enough value, then we can get similar to the previous solution, that is very close, like 0.375, 0.355, 0.305, okay. So our 0.305 is okay, very close to 0.3, and instead of 10,000, let us say we give a Ks of 1 million, then these displacements may be more closer to the exact values that we calculated earlier. Okay. Just to summarize, in this lecture we have defined the stiffness coefficient for a one-dimensional element. Then we form the equations for a single element, then assemble them for multiple elements, and then we have seen how to apply the boundary constraints either by exact method or by the boundary spring method. And then we can, once we apply these boundary constraints, we can solve the equations. Okay. Then we got the solution for nodal displacements and then the element forces. Okay. So actually this we have seen all the steps that we will undergo in any finite element analysis. We get the displacements and then we get the forces. Okay. So this we will apply for larger systems in the subsequent lectures, so that we understand the concepts. So this is my last slide, and if you have any questions, please send an email to this profkrg@gmail.com, and I will be able to respond to your queries. So thank you very much.